$10 and you can buy a DVD of any particular session. You can also buy them later, but later you'll have to pay shipping and tax and God knows what else. But you can just pick them up live here and take them home with you. So I encourage you to do that. They're all just sitting out there. Okay, so with no further ado, I'd like to introduce our panelists for the session on the Majesty and Magnificence of the solar system. And it's very difficult to have a panel on Magnificence and Majesty and just talk about it. So this is going to be a very picture-heavy session, and I hope you enjoy the pictures. On the far left here, we have Cynthia Phillips. Cynthia is a senior research scientist at the SETI Institute, and in addition to being a very prolific author of popular-level science books, she's also a planetary geologist, and she has been involved with the studies of Io, Europa, Enceladus, and the Galileo space mission. To her right is senior research scientist Mark Showalter, who is a rings and outer solar system planetary researcher as well. As far as I can tell, he's been involved in pretty much every outer planetary mission that there has ever been in one way or another. And he's also an avid image processor. And
I'm way too young for Pioneer.
He wasn't that much before Voyager. And through lots of prolific image processing, he has managed to discover 4 moons in the outer solar system, 1 of Saturn, 2 of Uranus, and 1 of Pluto most recently. He also happens to be my boss, so I'm being nice to him. Adjacent to me is Charles Lindsey. Charles is a multimedia artist, and he is the first and current artist in residence at the SETI Institute. You may have seen some of his work on Friday night when he did the music for Astrobiologist show very late after the after party, and he's been collaborating with both Mark and Eric Hansen, who you saw in the previous panel, working with various types of science images. So with no further ado, we can start our panel.
Okay, we are sort of planned an act of civil disobedience today in that we didn't follow the route of just each of us putting together a couple of slides to show you. We sort of merged everything, and we'll just work our way through it. I didn't know what Majesty and Magnificent meant. I know that I don't know where to go and buy a Majestometer, so we'll just do our best to show you things we think are cool, and if they are magnificent or not, that's up to you.
Yep, and as somebody who was attracted to planetary science because of the pretty pictures, you'll see a lot of pretty pictures today.
So why don't you just go ahead and, yeah, all right. Do you want to, we got a pointer here, and I
Excellent.
think maybe you would want to start with this one.
Sure, okay. So, I'm going to stand up because I can't really see it from sitting, so I apologize.
You want the mic?
Yeah, let me have the mic, okay. Sorry, so I'm kind of hogging the stage here, but this is some images of, since we're starting with the Magnificence and Majesty, the outer solar system, you have to start with Io. Okay, so I'm not an Io, I'm sorry, you have to start with Jupiter. I'm not a Jupiter researcher. You can see my bias. I'm a satellite person. But even I have to admit that Jupiter is really pretty magnificent. It's huge. It's a huge planet. If Earth was sitting in front of the Great Red Spot, it'd be about that big. So Jupiter is really big. If you added up the mass of all the rest of the planets in the solar system, you wouldn't get as much as Jupiter. So it's huge, right? And if you look at this great movie down here on the lower right, you can see that it has these bands in the atmosphere, and they actually move in opposite directions from each other. And so one of the great frustrations with the Galileo spacecraft that went out and studied the Jupiter system for a number of years was that our bandwidth was really restricted. So imagine, those of you who are of a certain age remember modems. You remember how, you used to dribble back, like if you were getting a picture and trying to download an email, it would come back just a few lines at a time. So imagine that's what it was like, except your transmitter was on Jupiter. We were sending back these pictures, they just dribbled in, and it was just excruciating how long it took to get them and how few pixels we could get. So with the Galileo mission, we couldn't make movies like this. We could send a single still image of Jupiter, but it took the Cassini spacecraft, which wasn't even going to Jupiter. It was on its way out to Saturn. It flew past, and it took these amazing movies that show how the atmosphere rotates. They show we've seen features merge. We've seen features, kind of the rotation rate change as we kind of get some shear between the different layers. So people who are atmospheric scientists find this just fascinating. And just from an artistic point of view, I think it's beautiful. And it has all these different colors to it. I don't know how good the color is out there, but it looks a little bit muted up here to us. But really it's bright, and these colors are close to true. If you've ever looked at Jupiter just through a backyard telescope, you can see some of this. You can see what it looks like. So Jupiter is, I think, certainly counts as magnificent.
I'm just noticing this now, but if you look through here, you can see a black dot.
Oh, yeah.
That's one of the shadows of one of the Galilean satellites. If you look over here, every now and then, one of those moons shows up. So that's just kind of the secret behind how this is done, is that there's actually a whole bunch of moons moving by at the same time that just happen to be caught in this image, and we'll see more of that in a moment.
Yeah. Okay, so I think what we'll do is we'll kind of go through a bunch of pictures, and then we'll take questions from the audience at the end. So if you have questions about these, start thinking about them, and we'll be happy to talk about our favorite topics and our favorite pictures and how we make pictures. But why don't we go through some more pictures first? So why don't you...
And before we go on, since you guys are involved intimately in choosing and talking about these pictures, I wonder if maybe we should give Charles just a moment here and give his take on this whole thing.
Well, my take on this, I'm highly influenced by scientific imagery, but the route I've taken, rather than trying to illustrate, I mean, how do you compete with that? You can't compete with that. And one of the things I share with Mark is I love to scuba dive. I'm also really interested in bioluminescence, which of course is a method of communication besides being aesthetically really interesting. And so in my own work, I'm influenced by these things, and I'm using organic materials to make the imaging aspect of what I'm doing. My sound is done with a lot of field recording, but I'm then processing it and making something else. It's almost artist as providing questions rather than answers. So that's my point of view, but what, I mean, are the pictures amazing? Of course they are. I mean, I'm really interested in this idea of, like what Cynthia just said, it's one thing when you're looking with a telescope and it's something like the augmented eye, but then when we're processing things further away that we can't see with our eye, and then choosing colors to define certain things, or assigning colors to aspects, that starts to get really fascinating as an artist.
So here are the 4 Galilean satellites. So from the left, we have Io, Europa, Ganymede, and Callisto. And so what I think is really cool about these is that the Jupiter system is kind of like a mini solar system. You basically have Io that's the closest into Jupiter. You have this elegant 1 to 2 to 4 resonance. So basically every time Ganymede goes around Jupiter once, Europa goes around twice, and Io goes around 4 times. This results in, and basically the orbits are kept from being circular. So the orbits are slightly eccentric. This means that the distance from Jupiter varies slightly, and especially on Io, which is the closest to Jupiter, it's the most volcanically active body in the solar system. So these bright colors you see here are mostly real, and I'll show you a quote, true color picture in a minute, but this is not some crazy scientist who decided to dye this thing yellow and orange. It really is kind of these colors. And notice I said kind of. We'll talk about that in a sec. But sometimes people call it the pizza planet, right? Because it kind of looks like, you have some olives and you have some tomato sauce and a lot of kind of yellow-looking cheese. But it's a really bright, vibrant place. And there's volcanoes erupting all the time. So next we have Europa, which is one of my favorite places. And it's this ice world. The surface is covered by a layer of ice that's about 100 kilometers thick. We think that part of the top is frozen solid, but under it there's liquid water. And so some of the images I'll show you of Europa in a little bit are just, I think, some of the most stunning of anywhere in the solar system. And then you move out to Ganymede, which has some portions are kind of old and cratered and look like the moon, and some portions are younger, kind of the brighter groove terrain. And then Callisto, it's not in this resonance, so that means that it doesn't have this source of heating. And it really is an old, battered, cratered world. Why don't you go on? So here's Io. And so remember I was talking about true color versus false color versus pseudo color or enhanced color. There's a lot of words that we use. And so I was a grad student on the Galileo imaging team, and so I was fortunate enough to get to work with some of the data just as we got it down from the spacecraft. And one of the things that I worked on was combining, it's not like it's not like you have color film, for those of you back in the days of film, where you take one picture and it's in color. With this, or even a CCD, a digital camera, this is like a digital camera, but you take exposures with different filters, and then you combine them together to make color. And so people always ask me, if you were actually there, what would these moons really look like to your eye? If you were in a spacecraft looking out the window, peering, everyone else is watching the boring movie, and you lift up the shade and you're peeking out, you want to see what Jupiter's satellites really look like. What would it really look like? And that's a really hard question to answer, because remember, you're 5 times further from the sun than we are here on Earth. So it's pretty dark. So you'd have to stare at it for a long time. And then you have to kind of compensate for that. And then you basically have to kind of sort of recreate what this would look like. And so the image in the top right there of Io, that's our best guess as to what Io would really look like if there was enough light to really see it. Okay, and so maybe you'd have to bring a big spotlight or something with you to be able to get a good view of it. But the colors are basically real. And so what's going on there is you have these yellow areas, these red areas. Those are mostly different compounds of sulfur. The sulfur is being erupted from these volcanoes, and then you have these dark lava flows that are made out of more silicate materials. And then you have some of the bright white stuff, and that's sulfur dioxide frost. So this is an example of an image where it's a pretty picture. It's beautiful aesthetically, I think, especially if you like yellow. But it's scientifically useful, right? It's not just color gratuitously. It's really telling you something about what the surface is made of. And so then this image here on the left, this is one that I personally made, so it's one of my favorites. And I think it kind of looks like an orchid. It's like a flower, right? But this is actually a volcanic system on Io called Coulon. And so what we're seeing here, again, is that the colors are tied to different compositions. And so you can see that there's kind of a difference in stretch between the two. The one on the top right, that's the more scientifically accurate. The one on the left is the pretty press release, let's get the cover of Science magazine kind of picture, right? So you stretch it, you play with the colors of it. So it's still accurate, but what this does is it really brings out the white. So you see, here's these white regions where there's lots of frost. And then here's this red plume deposit of short chain sulfur. So that's like S8, like 8 sulfur molecules stuck together. And then you have these green areas that are a different form of sulfur, and the yellow and the black are the lava flows. So again, it's still scientifically accurate, but it's not quite as true color. And then the image in the bottom there, that's a plume that's actually erupting. So again, this is a flyby, and Mark can tell you more about how this image was made. It's really cool, but it's a volcano called Tvashtar, and it's right up near the north pole of Io. And we were fortunate enough to get a little movie of it actually erupting.
Yeah, I'll just say very quickly, this is the only movie that exists of a volcano erupting on a body other than planet Earth. And the reason it exists is totally by accident. The New Horizons spacecraft did a flyby of Jupiter on its way to Pluto. It gets to Pluto in 2016. I hope I got that right. So I was on the team that was planning the flyby of Jupiter, and I was doing the ring observations. Now, Jupiter has a very faint ring system, and you can't see it, but it's kind of right here, goes across the image. I realized when I was doing the plan that there was going to be this weird Kodak moment where Io, on the far side of Jupiter, was backlit by light reflected off of Jupiter. That's why you can see the dark side of Io here. And then this is actually sunlit Io on this side. When we did this flyby planning, we didn't know that there was going to be an enormous volcano erupting while we were flying by. So nobody thought of actually making movies. But I, completely accidentally, thought, well, wouldn't it be cool to just get a sequence of images of Io passing behind the ring? Roughly speaking, they seem like they'd be about comparable in brightness. It turns out, obviously, that you can't see the ring because it's much fainter. But so an accidental movie that was mainly just to show something that you can't see, the rings and Io, is the only time we actually caught a movie of an erupting volcano.
Cool.
And so you'll see lots of pictures of rings later. But in Mark's point of view, rings are really the only reason to take images of anything. So.
I intentionally took Io.
but only because it was in the way of his pretty ring.
Okay.
Yeah, good. Oh, what the scale is of the volcano? Oh, I don't know that offhand, but it's pretty big. Io is about Io is about the size. It's a little bit smaller than the moon, but not that much smaller. So it's a pretty big world. And then it's probably 10% of the radius or something?
Yeah, I think I was about 2,000 kilometers.
2,000 kilometers?
Something
Yeah,
like
it's big. And remember, Io has pretty low gravity. So it's not like, and there's no atmosphere to get in the way. So if you eject something, it's going. It's, it's a pretty sizable volcano, but you wouldn't get something that big on Earth easily. Okay, so let's go on. So this is Europa, and this is one of my favorite places in the solar system. So, and again, this is another image that I made, so it's one of my personal favorites. And so if you remember the image of Europa before, Europa is really, it's very bright. It's one of the highest albedo bodies in the solar system. So that tells you, again, something about the composition. The composition of Europa's surface is primarily water, frozen water, water ice, frost. But we have these non-ice, and I used to call them non-ice contaminants. And actually, Frank Drake yelled at me for that. And he said, don't call it contaminants. That's the most interesting stuff. It's not contaminating. So I'm calling them non-ice components now, because that was good advice on his part. But so when we're taking images of Europa, the ones here on this side, these are some nice close-ups. So you can see that we have cracks, we have ridges, we have this one right here, kind of looks like a puddle. Can you guys see that? It's like this smooth spot, this little this little dimple in the middle, that's actually a crater that just happens to be there. That's coincidental. But this smooth spot here, some people think is some kind of, it looks like you flooded, you had some kind of liquidy stuff flood out over the surface. And the problem, of course, is that liquid water isn't stable at the surface of Europa, so people are pretty puzzled. But when you're thinking about places to land, that's a nice smooth place. That would be a good place to land. And then in this bottom image here, you have things that look like icebergs, but these are really big. They're a lot bigger than icebergs here on Earth. But so this is what Europa looks like kind of in black and white. Then if you try to make it into color, so again, this is where that enhanced color comes in. So one of the things that we do, one of the games that we play is that normally when you see in color, if you see a color combination image, it has like red, green, and blue, and they're combined together to make it look like it's in color. Well, this isn't red, green, and blue. Instead of red, we have a near-infrared filter that's almost at like 1 micron. So you're stretching the red out further than your naked eye could see. And then instead of blue, we have violet. So this image here is a near-infrared green violet. So basically what we're using is the color, we're expanding the range that you would normally see in a color image, and we're putting more information into this image than you would normally see just with your eyes. And this image is also very stretched, very enhanced color-wise. And so Europa's surface, really, if you looked at it, it's basically white. It's very bright, it's very white, has kind of a little bit of yellowy, browny stuff on it. But these ridges here, what we can do is you see that these linear features are all red. That means that those are showing those non-ice components I mentioned. There are a lot of hydrated salts or maybe sulfuric acid, talks something about the communication with the subsurface. And so you can really use the colors in this to do science. But I worry, sometimes people try to map out the red and say, oh, okay, that's plankton or something. They match the spectrum of this image to something from their lab. And I was like, no, this is a pretty picture. It's for press release, right? And you could do some science, but you have to know where your data comes from. So I always get really incensed when people start trying to do science off of these press release images. You guys want to say anything on Europa, or should we go on? No. Okay. So I'll say a little bit less about Ganymede and Callisto, not because they're not so interesting, but just because they're not quite so colorful. And so this is a mostly true color picture of what Ganymede looks like. So you can see it's really much more brown. It has some kind of bright places where there are some more recent craters. The surface is basically a combination of this old, heavily cratered dark terrain and then this younger groove terrain. And so what we're really seeing is a combination of the older terrain where nothing's really happened, and then some of these newer tectonic features. That's these linear features that you see also in this top image here. This is a 3D model that's based on some of these images. And so what we see is that kind of the competing effects of Ganymede being further out from Jupiter. It has some tidal heating, but not as much as Io and Europa. Fun. And then finally, Callisto. I once did a project in graduate school about Callisto color, and I got mocked by the other graduate students because they're saying, Callisto has no color. It's so boring. Why are you doing color in Callisto? But, it has some color, right? I mean, this is Callisto in color over here in the top. And, there's some parts that are browner and a little bit redder, but yeah, they were right. Compared to somewhere like Io or even Europa, it is pretty boring in color. But one of the cool things about Callisto is that you have these giant multi-ring impact basins. So can you guys see there's kind of concentric rings in this image? Looks like a bullseye. So that's these puzzling features. We had an impactor, a body come in, smack into the surface, and instead of forming a big crater, this was so big that we think get penetrated to some subsurface layer, and you get just these concentric rings around it. And we also have these crater chains. So there's a linear feature up right here. That's where a disrupted impactor, kind of like Shoemaker-Levy 9 that broke apart into a bunch of pieces, this is one that crashed into Callisto, and it made this nice chain of craters. And then another thing that happens on Callisto is something called thermal segregation, where basically you have dark stuff and bright stuff. So what happens is that the dark stuff absorbs a little bit more heat. It drives off the slightly more volatile, like the ices. Those sublimate a little bit, they go into a gas phase, and then they get deposited on slightly higher spots, like the edges of these craters. And so over time, you have this division where the dark stuff stays in the bottom and the bright stuff kind of goes on the ridges. So again, that's something where we can use just the color, just something as simple as the bright and dark contrast in this image to really do some science. Okay, and I'll turn this over to Mark.
Yeah, I wanted to carry on a little bit with Jupiter. One of the hats I wear is as a data archivist for NASA. I run one of the components of the planetary data system where we distribute the data to planetary scientists that comes down from all of NASA's missions. We have been reprocessing some of the old Voyager data going back to now 1979. I realize some of you weren't born at that time, but this was the first flyby of Jupiter in which we had a good camera. And we are finding just beautiful stuff in this data archive that people more or less forgot about, probably 29 years ago or something like that. And dredging it up out of the archives, there's just marvelous stuff in there. This is just a couple of images I put together. I didn't do the kind of work that...
Got to work on your mosaicing there, Mark.
Pardon?
Got to work on your mosaicing.
Yeah, obviously,
your frames
I
are really
did this
ugly.
very quickly, but mainly it was just to see what was there. And what we have here are the clouds of Jupiter, close-up version of what that little movie was showing a few minutes ago. And there is Europa seen in front of Jupiter, so you get a little bit of a sense of scale of the two. But there are literally probably 1,000 images like this, maps of the entire, you could piece together the entire planet Jupiter from what we have in the archive in color based on what's available. And you see these psychedelic patterns just everywhere.
Can I just interject? One of the things that Mark and I talked about, and there's been a video running in the arts room, which is Cassini imagery that Mark provided and then I worked with to process. One of the things when we were first speaking about it, which is why I actually like this, and I love the Apollo period mapping of the moon where you actually saw the grid. And I like where the media actually shows the process of collecting the data. So when Mark and I started looking at things, there were things he'd say, oh, that hasn't been fixed up or cleaned up. And there were all the glitches that really spoke of the process of collecting. And I really like the rawness. I like to see the artifacts of the collection itself rather than really like paintbrushing, smoothing everything out. So.
Yeah. Okay. Want to move on, Rob? Okay. I'm working on the Cassini mission to Saturn, and I just put together a few excerpts from some of the highlights of Cassini that I could find in the archive. And I'm not an expert on many of these things, but you wanted Magnificence, and I'm doing my best to keep the crowd happy. There is a storm going on just right now on the planet Saturn. One of the things that comes out of the fact that Cassini has been at Saturn since 2004, and with luck will be continuing to function until 2017, we will have an entire 1.5 seasons of the life cycle of Saturn. It's got a 29-year Earth year period. So we can't stay there for 29 years, but we can stay there for more than one season anyway. But this storm erupted a few years ago. It's still going strong. The temperatures in the highest levels of that storm are almost room temperature. So even though we're out at 12 astronomical units, 12 times the distance that Earth is from the sun, there are some very warm temperatures, basically material being dredged up in basically a long, ongoing storm, temperatures and material being dredged up from the warmer interior of the planet. So, move on. Saturn has its own solar system of little satellites as well. This is Titan. In the visual light that our eye can see, it is basically a yellow ball, nothing more, because it's got a very dense atmosphere and we cannot see through it at visual light. But we have infrared instruments as well as ultraviolet instruments on Cassini, and the infrared instruments can see through the clouds. I thought this was a really remarkable image that came down just a year or so ago. This is the infrared instrument looking at the planet, looking from the dark side, And of course, everybody, the first thing you notice is that very, very bright spot. It's essentially a single pixel in the infrared instrument, and it caught everybody's eye. What is going on there? It turns out that we had already suspected, and this was essentially the confirmation, there are lakes on the surface of Titan. They're not water lakes. They're made of basically a mixture of liquid methane and some other things. But one of the things that is universal about lakes everywhere is that the surface is flat. A rocky surface is very rough, and it kind of gives you a diffuse reflection like a gray piece of paper or something like that. But when something is smooth, you get glinting sunlight. You get basically perfect reflection off of the surface, what's called specular reflection. And this is an example where we had suspected there was a lake up there, and based on the geometry, what we were seeing is the sun reflected off of the surface of that lake. So just a kind of nice shot to think about. All right. Probably everybody's favorite moon of Saturn today is Enceladus. It is the one that has a great deal of, I won't call it volcanic, it's probably more like geyser activity, mainly in its southern hemisphere, mainly near its south pole. This was an image that we pulled out of the archive not too long ago. I don't think NASA ever released it as a press release, but we found it in our archive, and this is my very crude, I'm not really happy with the color, but you know, what can you do? What you're seeing, though, are flat sheets of material coming out of cuts in the southern pole of Enceladus. And because of the lighting, you're seeing essentially the shadow. Let me maybe point at it. Because of where the sunlight is, you don't, these sheets of fine dust and fine ice crystals basically don't get illuminated until they get up to a certain height. But once they do, they are now in sunlight and you see them glowing like this. And in fact, you see several lines cut across. Those are actually different sheets of material from different cracks at different distances from the observer. And it gives you a little bit of a sense of depth there that I think is quite beautiful. All right, this is Rhea, and I believe Cynthia has to talk about it.
Yeah, so here's something else you can do with pretty pictures, if you have enough of them, is that you can actually make 3D models of a surface. So one of the projects I've been working on is working with images of craters on the satellites of Saturn from Cassini images. So this is a crater, the top left one, that's actually on Tethys. It's a pretty large crater. And if we have multiple views of the same crater, we can combine them using stereo software to make these digital elevation models. So that's what this image here in the lower right is. And so what we see in this image is that we've taken the view of the surface from these two different angles. You run it through a very sophisticated computer program that lets you reconstruct what the 3D shape of the surface is. So you basically make a shape model. So then this is a particular rendered view of that shape model, and then we've draped the actual image back over it. So you're seeing a combination of the topography and the model of the shape of the surface. And so most of these shape models that you see, they have a lot of vertical exaggeration. So if you've ever seen these 3D views of the planets, everything looks really tall and really steep. This doesn't have vertical exaggeration. So this crater, the walls of this crater are really, really very steep. But what we're interested in more than that is how shallow this crater is. So the reason we're doing this is to study something called crater relaxation. So we have models for how deep this crater should have been when it formed. So we compare our model of how deep that crater should be with actual measurements. We take profiles across the crater, and we see that the crater is very shallow in the bottom. We use that difference, the difference between how deep we think the crater should be when it originally formed and how deep it is today when we measure it. And that helps us to give us some clues that we used as inputs into our thermal models. And so those models are basically a model of the temperature of the subsurface, and this is Rhea right here, so of the subsurface of Rhea throughout time. So we can say that at the time that this crater formed, the subsurface was a lot warmer than people thought it was. So if the subsurface is warm, then the ice flows, and it basically flows and it fills in the hole. So if you think about making a hole in the sand on the beach, some of that sand will kind of flow in, and the hole won't be as steep as it was originally, especially if the sand's kind of dry. And so in this case, it's actually the ice, the warm ice that's flowing to fill in some of the bottom of this crater. And so we use that to say that we think that when craters like this formed on Rhea, and especially on another moon of Saturn, Dione, that there could have been an ocean layer under the surface, under the ice layer, there could have been liquid when these craters formed. And of course, these craters are really old, so we're not necessarily saying there's water there today, but there could have been water in the past. And so that's interesting for the people who do these theoretical numerical models.
Okay, a couple other recent results from Cassini. This is something I find particularly bizarre. You've seen a couple of satellites by now. Some of them are big spheres, some of them are small, but they all have craters. And this is a moon of Pluto. It's called Methone. It's only about 2 kilometers across. And I'm sorry, did I say, yes, moon of Saturn. It is called Methone, and it is actually also the body that you see right here. It's embedded in a very, very faint ring of dust. But it's an egg. It's pretty much just an egg, perfectly smooth as far as we can tell. This appears to be a totally different class of object, something that astronomers call a rubble pile. There is no strength here. It is essentially probably got some kind of a little rock in the middle of it that's got enough gravity to hold on to some dust. And the dust basically collects around it, but it basically flows. It's almost as if it were a liquid. And gives you a perfectly smooth surface. If some other object from outside came in and collided with this thing, it would probably just blow apart like a big puffball or something. And then over some period of time, it would eventually reaccrete into what we see. But it's just a remarkable thing to see in such a different contrast from the cratered rocks that we see so much of.
And is it really that egg-shaped, Mark?
Yes. It is actually, the people who study the gravity of these things say it is basically, it's the shape that a ball of water, essentially a little glob of water would take. It is called hydrostatic equilibrium. It is exactly the shape that you would expect it to be if it has no strength at all. Okay, now unfortunately my movie isn't going to play, but if you saw the lightning talk, I played a bit of this the other day. One of the really remarkable things we found in the rings of Saturn just a couple of years ago is a set of grooves. These are vertical ripples in the rings of Saturn, and they go off across a whole swath, thousands of kilometers of the ring, with almost perfect periodicity. I don't know how well you can see that, but wherever you look, even if you go on one side of a gap, you've got the ripples and then a gap, but then the ripples pick up again at exactly the same periodicity. This was one of the pieces of evidence we had for a cometary impact into the rings of Saturn, which was very similar to the case of the rings of Jupiter having a similar ripple pattern. We were able to associate the ripple pattern in Jupiter's rings to the Shoemaker-Levy 9 impacts, a large comet that hit the rings in 1994. And this feature appears to be indicating that there was a different impact into the rings of Saturn, and we can unwind the spiral and track it back to sometime in late 1983. So shortly after Voyager left the system in 81, something hit the rings, and here we are in 2012, and we are still seeing the ripple pattern left behind from that impact. Right? Rob's favorite ring, I had to throw it in. In fact, I think you used this image.
I used the same image.
Yeah, I just picked this out separately, but it shows some really cool things about the rings. One is a good friend of mine, Pan, I believe is right there. It's a moon in the middle of what's called the Yankee Gap, and it's creating this ripple pattern, and you can maybe see some little spirals coming off of it. This was a pattern that we actually saw in the Voyager data, and we used this to infer that there must be a moon there, predicted where the moon was, and then found Pan. So that was kind of a fun sequence of events of seeing a pattern here, and then inferring the moon, and then looking in the Voyager data and finding a moon exactly where I expected it to be, which was very gratifying for me, of course. And now we're seeing it on a regular basis in the Cassini data. The F ring is the one that Rob's been studying. It's got a moon near it called Prometheus that creates these weird, very strange patterns in it as well, very similar. But just a quick illustration in one image of some of the really interesting dynamics that we're seeing in this system. I'm sorry, that's Pan over there. What am I saying? Yeah, okay. All right, let's see. I had a little bit more about the F ring. Unfortunately, my movie won't play. But here you can see Prometheus close up. That's its full size, and there it is relative to the ring. And this is some of the damage that both Prometheus and some of the other moons and bodies nearby do to create this very, very chaotic looking system that never ceases to amaze people who have been watching it now for well over a couple of decades. All right, Cynthia and I felt that if we're going to talk about the outer planets, we really shouldn't stop at Saturn. The trouble is the amount of information we have drops precipitously as you go beyond Saturn. There are two more giant planets, Uranus and Neptune. They're very interesting bodies unto themselves, but because NASA or anybody else has ever sent a spacecraft there to hang around for a while, we don't have nearly the body of data, and we don't just know all that much about them. Uranus was essentially a cue ball. It was a perfectly bland sphere when Voyager got there in 1986. That was basically the peak of winter, however. And as time has gone on, it's kind of warmed up. And one of the things that happens when it warms up is storms start to form. So all these little dots, these are now taken from an Earth-based telescope in Hawaii, are actually storms, active storms on the surface of Uranus, something that we didn't know were there back in '86 during the flyby. We also have this lovely set of images of the rings, a set of narrow, very slender rings that are circling the planet, and this is a set of seasonal images showing the rings going from how they were, this must have been circa 1990 or late 80s, and going on then to 2008 when we had an equinox on Uranus and its rings were edge-on. Okay. Now, I've done a bit of study of the Uranus system and was very excited a couple of years ago to discover two new moons, which are in these green and red circles up near the top. And when we processed the data a whole bit further, we actually found two faint rings, one right here and one right here. The outer rings, these are the inner rings that we already knew about, but these two were discoveries from Earth-based observing. They were not seen by Voyager. Although the one in the red circle up there, once we knew where it was, I was able to go back to old Voyager data and find it some 20 years before the time that it was officially discovered. But what we're finding about this system, among other things, is that this is a chaotic set of satellites. These satellites do not have entirely predictable orbits. They bounce off each other in the sense of tugging at each other's gravity, and as a result, over time, these things basically change in their orbits, and it's a very mysterious process. The smallest moon we know of, the one in the green circle, is called Cupid, and some work we've done shows that it's only going to live another, maybe 500,000 years before it bashes into a bigger moon called Belinda, which I think is the brighter one below to the left. So what we have is a very evolving dynamic system in which we may see moons that last only millions of years, but because things eventually break apart, probably making this little ring for one thing, you basically get a situation where moons break apart to become rings, rings reaccrete to become moons, and over time all that material stays around, but what moon it's in at any given time changes over time scales of even 1 million years. Okay, and Neptune. Of course we have to show Neptune. This is going back to Voyager data. The great dark spot of Neptune, no longer there based on what we can see from the ground today. But at the time, it was very much a raging storm, very similar in some ways to the red spot of Jupiter. But the difference is the red spot of Jupiter has been there for well over 300 years now. And this one lasted maybe a few years, 5, 10 years, probably not much more than that. We also have a couple of rings, very faint rings around Neptune, and one of them is very distinctive in that it is not a complete ring so much as a set of arcs, short segments here. You can see 3 of them. There's a 4th one off to the side. And we've been watching these a bit over the years. They've been very difficult to detect from Earth, but using Hubble we can now do it. Here's an example of some work I did with Hubble a couple of years ago, and that little arc is basically that arc. So we're seeing it, it's still there some 24 years later. The difference is it's much shorter now. It seems to be basically a short-lived piece of the system, probably not going to live another 10 or 20 years at the rate it's going. But it just shows that these are very, very variable systems. They're not sort of perfect systems that last forever. The way we understood rings when I was a kid was they've been there for 1 billion years and they'll be there for another 1 billion years. And we're seeing actually things changing on timescales of decades and years now. And finally, I have to finish up a little bit with Pluto, just because I did some work on that just last year and we're doing more right now. Here is one of the actual images I got from Pluto last year. If you look very closely, you can see one moon called, this is not working. Right up there is Hydra. Somewhere over here, I think it's that one is Nix. And I think I'd have to check on the map. Well, okay, it's over here. With a little bit of processing, there's a little dot. You can barely see it over there. And that was the discovery of the 4th moon of Pluto about a year ago now. This has been of great interest to the planners of the New Horizons mission on their way to Pluto. because we suddenly realized that we don't know what's in that system anymore. We have underestimated Pluto. It may be a dwarf planet, but it's a very interesting dwarf planet. And if we're going to send a spacecraft through this system, we have to know what might be in its path. And as a result, we are doing some very, very extensive searches of the system right now with the Hubble telescope, probably running from a week ago to a couple of weeks from now. We'll actually have some more information about what might be there in terms of small satellites and dust, mainly with an interest of what might be a hazard to the spacecraft that's going to be flying through that system in 2016. Okay.
Are we done? Okay, and with that, we can open it to questions from the floor. We have a roving microphone here, and if you would raise your hand, we'll bring you a microphone. Right in the back.
It's so amazing, it's hard to come back.
So after the sun eats up, I believe it's hydrogen and it goes into dwarf, I guess it's dwarf phase. What's the outer solar system going to look like, and maybe even beyond, like the Oort cloud?
You want to take that one?
Yeah, that's a very good question. It depends on whose model you believe, right? So there's different models. The sun will basically, it'll eat up all its hydrogen. It'll burn helium for a while, but it's not really big enough to get all that far down the sequence of basically other things that it can burn. So yeah, eventually it'll be a red giant. It'll probably envelop, depends on, there's models that say it'll basically reach the orbit of Mars, maybe the orbit of Earth. But yeah, there will probably be a brief time when the outer solar system is nice and clement and habitable, but it won't last very long. There's been some great science fiction about everyone migrating out to Europa and the ice melts and you get this thick atmosphere and it becomes paradise, but that's not going to last really very long. It's not a very good long-term plan, I would say.
Yeah, the one thing all the models do agree on is it's going to be very bad news for Earth.
Yeah.
Has there been any talk about possibly any funding or anything for a orbiter or lander to Uranus or Neptune?
I'll take a stab at that. Every 10 years, the planetary community does a survey of what would be the next really great missions to do. Sometimes, most of the time, but not always, those recommendations then get followed and become reality. That was how the Cassini mission came to exist. There is a lot of work being done right now on a potential mission. Actually, the Europeans have now planned a mission to Jupiter and will eventually go into orbit around Ganymede. And we'll be doing some nice close flybys of Europa in the process. So that was basically something that was envisioned out of the last decadal survey and is now coming to reality. The most recent decadal survey did rank a Uranus mission very, very highly. It was kind of a surprise to those of us who care about Uranus that it ranked so highly. But what that means is that probably there'll be some studies going on in the next 10-ish years, and then possibly a new start in the decade after that. But the idea is not to just do a flyby. A flyby is, I won't say easy, but it's easier because you don't have to stop once you get there. The tricky part of any planetary encounter is stopping because you have to take big rockets with you to slow down. And that's what makes these orbital missions very expensive and very difficult to pull off. But I think Uranus is very highly ranked on everybody's favorite list as something that will be a target probably in the next 2 decades.
Enceladus, I was noticing the markings on the surface there. Did that imply that there's an ocean underneath Enceladus?
That's a very good question and a topic of speculation. So Enceladus, it's this little tiny rock. I mean, it's not as small as some of the glorified ring particles that Mark likes to show and call moons. But it's really not very big. It's not a nice big proper moon like in the Jupiter system. So it's this.
These are fighting words, you know.
Yeah. Okay. I'm just trying to provoke you. We need some action.
All right.
Yeah. So there's really no excuse for Enceladus having these giant plumes. And I would say before the Cassini images, we knew Enceladus was really bright, but we didn't know that much more about it. And so what we've seen is that, we have these amazing geysers that are venting material out of the South Pole, and then we see there's these cracks and ridges, but that's really only in the southern hemisphere. If you go look up at the north part of Enceladus, it looks old and cratered, and it hasn't had nearly the degree of activity that's been going on in the south. Now remember, this is this little tiny moon, so And it's not in a nice, elegant resonance like the Galilean satellites. So really, people were puzzled and surprised. And that's the best thing about planetary science, is when one of these moons, either it's you find a new moon where you didn't think there were any, or a moon you knew about is doing something completely crazy that you have no explanation for. I mean, there's a variety of models. I don't find any of them all that satisfactory, but probably there could be, one of the ones that seems probable, although not definite, is that, yeah, there's some kind of localized layer of liquid water down near the south pole of Enceladus. So under the surface, there could be a reservoir of liquid.
Yeah, I'll just add to that, particularly since I've been provoked. This may be a case where the ring scientists got there first, so I'll just have to trumpet our work a little bit. But there's a ring that I didn't actually show a picture of, a very faint dusty ring called the E Ring of Saturn. And its orbit is coincident with the orbit of Enceladus. And so ring scientists have kind of known for, going back, actually this was a ring that was discovered in 1967, and was looked at very closely in subsequent years and by the Voyager flybys. But everybody knew from kind of day one that it was a very faint dusty ring, but it peaked. Most of the material was right at the orbit of Enceladus. So there's been speculation actually going back a couple of decades that there might be something like geysers on Enceladus, but I guess maybe we didn't think in terms of actually seeing the geysers quite as clearly and as beautifully as they've been imaged by Cassini. But when I saw one of those first images of the geysers of Enceladus, geysers is the wrong word, but they're just plumes. We don't really know the mechanism. But when I saw that first image, I said, oh, okay, now we know where the E-ring comes from. While everyone else was running around writing papers about this great, awesome discovery, it was like, hey, we knew about that already, but it's still awesome, no question.
Could you give us an update on the Voyager and Pioneer spacecraft?
I am not an expert on that. I can tell you that Voyager is still up and alive and running, but every instrument has been shut down, including the cameras, with the exception of the magnetometer and there's, I think, a plasma waves instrument that's still functioning. And I believe every 6 months or so, they communicate with Voyager and they get a new download of data. So we know that it's crossed the heliopause and it's basically out into the space that is no longer dominated by our sun. But, and it's still operational, it's, but at a very low level, of course. And Pioneer, I'm sorry, I don't know too much about that. I don't even recall hearing recently about any communication.
I thought the last attempt to contact Pioneer 10 was unsuccessful.
Yeah, I could believe that.
Because they were using it as kind of a test for, I know the ATA was doing some communications with that, looking for that signal.
Right. Yeah, so I think Pioneer is no longer with us. I think the Voyagers are actually still functioning, but at a very low level and still sending back some good data.
If you do get a trip to Uranus, are there any particular experiments you can use to find out why it's flipped on its side? I mean, how would you detect it? What caused that?
That's a good question.
Yeah.
It is certainly an object that stands out. I showed images of it rotated sideways, in part because it looks cool, but in part because it really is rotated sideways. Its pole is actually a little bit south of the ecliptic plane that all the planets orbit in. There's speculation that it was some kind of early planetary impact that carried enough angular momentum to basically switch the rotation pole. It's probably been that way for a long time. It's probably essentially going back to the time when the whole system formed, that it's been oriented that way. But the best I can say is that people believe something hit it, basically, that there was a lot of material floating around the outer solar system in those days, and it was not maybe impossible for two objects to collide and result in something like that. I will also note that the Neptune system, although it's rotating in a more or less, quote, normal way, it actually has a major satellite called Triton that's going backwards. And that also is something that indicates some kind of major collision disrupted that system probably very early in its history.
Does Uranus have any moons?
Well, yes, it has, actually, very briefly, it had more moons than Saturn. But only, they are in the equatorial plane, which means they are going around sideways like everything else. Yeah.
Here's the question. Since Pioneer, you've had images of the belts of Jupiter over 30 years or whatever. What do you see in the evolution of at least the character of the belts over this long time span?
Just to clarify, by belts, do you mean the rings or do you mean something different? Oh, the cloud belts, I'm sorry.
Rings.
Yeah, rings.
It's your ring bias.
Yes, okay.
Yeah.
Go ahead.
So I would say on Jupiter that it's been surprisingly stable, actually. There's been some variation in the edges, but the Great Red Spot, like Mark said, it's been seen from ground-based telescopes for hundreds of years, which is a really long time for a single storm system to be stable. We've seen some changes where there's these white ovals, and we've seen them, we've seen new ones form, we've seen them merge together. And I'm not an atmospheric dynamicist, so I'm afraid I'm not up on the details of any changes in the actual, belts.
Yeah, I do know that some other astronomers have been using the Hubble telescope to observe the southern hemisphere of Jupiter in particular, because essentially 3 very bright white ovals merged a couple of years ago, and apparently that seems to have triggered something where the entire southern hemisphere of Jupiter seems to have gotten brighter, and there seems to be some things going on there, but I'm not the expert on that. I just know that major astronomical resources are being devoted to the question.
Given the dynamism you're seeing in the Saturn's rings and in the other ring systems, what's the current thinking on how long the ring systems have been there, when they will disappear, whether they can become full-fledged and go away? What's the evolution of ring systems?
That's such a great question. Because the answer, all these years into the Cassini mission, the consensus of the rings community is we don't have the vaguest idea. There are 2 issues that sort of contradict one another when you get to the rings of Saturn. They're very bright and very prominent. I mean, let me just add, Jupiter, Uranus, and Neptune all have rings that are very narrow, very slender. It's probably not hard to make them very, very old. They could have been around, they're basically debris left over, still hanging around from when those planets formed. Saturn's rings are way too bright for that. On the one hand, there are a couple of mechanisms why they can't be that old or that bright. If they were around that long, they would have been frittered away or made very dark, which is what the other rings are. On the other hand, if they are young, you have to make them out of something, and we don't know what that could be. You'd have to break up an object comparable to Mimas, that is maybe just a little bit smaller than Enceladus, in order to create the entire ring system of Saturn that we see. So we still don't have a good answer. One of the things we're going to get a handle on coming up later in the Cassini mission is the mass of the rings. As Cassini missions wind down, it will basically fly into the gap between the rings and the planet. By flying so close to the rings, we'll actually finally get a measurement of the mass of the rings, which is something we really don't know. And that will say how much material is there enough for it to have been around for a very long time, or if it's a small amount of material, then they have to be young. But if there's a small amount of material, then it's not hard to make them. So we'll know more. So stay tuned as best I can say. We should know in maybe 5 years a whole lot more on that question.
Hi, my name is Tom, and my question is about a little bit of a historical perspective on exploring the outer planets. And we talk about Voyager just leaving the solar system. Over the past 30 years or so, are there any predictions that you think that we got really wrong, or is there something that has come up that's really, really surprised you? We've gotten, no more space shuttle, and we've had budget cuts, but we have much better understanding of these rings, and new moons have been discovered, and ideas of liquids and things like that. I'd just like to hear some comments from any of you.
Well, I think that Titan has turned out to be one of the more interesting places. We knew from ground-based observations that it had a pretty thick atmosphere. And when Voyager 1 first went by it, the trajectory was intentionally set so that it'd have a nice close flyby of Titan, because it was going to be really exciting. We'd see what the surface looked like, and it turned out to be really disappointing. It was that orange ball that Mark showed. That's what it looked like. And so all of the atmospheric scientists were all happy because it was this, big, thick, hazy orange ball, but the geologists were kind of disappointed because it was a big, thick, hazy orange ball, and you couldn't see through that to the nice surface that was under it. And so fortunately, they got that information in time to divert the trajectory of Voyager 2, so that instead of Voyager 2 wasting another flyby pass, a close pass by Titan, they could send it on this grand tour, and it could continue out to Uranus and Neptune. So I think that was, that was fortunate that we got Voyager 2 out there And also that we learned something about Titan so that the Cassini mission could have some filters that would hopefully see through the atmosphere of Titan. They could have some instruments like the radar that's proved to be fabulous in actually mapping out the surface. And then Cassini also had the Huygens Probe that actually landed on Titan. It went down through this cloud layers. And when the Huygens Probe was built, we had no idea if there was going to be liquid on the surface or solid. I mean, it could have been a global ocean of methane. That was one of the possible models. And so they had to build this probe so it could survive and do science if it landed in water, or not water, but if it landed in liquid, or if it landed on a solid surface. And I really think that Huygens is one of our triumphs of outer solar system exploration, that they managed to build this thing, that it worked, it landed, it survived the landing, and it kept transmitting for as long as Cassini was in range to receive data. It was, unfortunately sending the same picture back over and over, but it was a really very successful mission.
Yeah, I'll just add, I mean, in my particular field, I think the way I would sum up the biggest change in the way we think about these things is the fact that everything changes over timescales that are much, much shorter than we ever had any idea. When I grew up, the rings were very flat, very uniform, and we had essentially the same rings today that we had a billion years ago, and now we don't have the same rings that we had last Tuesday. Things are changing in timescales of every one timescale you can imagine, and so that's caused a lot of rethinking of how that all works. Yes.
Hi, I had a question about the New Horizons mission. Right here.
Oh, there you are. Okay.
Yeah, I was just wondering how long the flyby will last and how many images will hopefully get taken and what questions about Pluto we can hopefully answer.
Yeah, it is going very fast. It is a very fast spacecraft because that's the only practical way to get to Pluto, which is very far away, obviously. So it will be a very fast flyby. Probably the best imaging will come down over a period measured in hours, not even days. And so it's going to be a very, very fast operation. They are spending a lot of time thinking about how it's all going to work because they have a lot of things to point at. They don't know what's interesting because it's a very, very mysterious place. The other thing I'll just warn you about is that it is going to be a mission for the patient because all that data gets gathered during the flyby, and then we have to wait a year or more for most of it to come down. There will be a slow trickle of data, but it takes a long, the farther the spacecraft is away, the slower it has to send its data down. And so we are just going to have to wait and wait and wait and see we'll get some of the best pictures pretty quickly, but the rest will take some time to come down. I have not been that involved in the planning of the imaging sequence and so on, so in terms of how many images, I'm afraid I couldn't tell you that. But they are certainly, they've got infrared instruments, they've got visual camera. They're going to be looking for features on the surface. They're going to be studying Charon and Pluto. And of course, they're going to be getting the best images they can of some of these other little satellites that are around. They will, I'll just note, because I'm biased, that they will be looking for a ring, although they haven't seen one yet. But the fact is that it's going to be a very, very compressed flyby. And it'll be awesome data, but it will not be a lot of data. So just be prepared for that.
Yeah, and I would imagine the number of images we measured in what, dozens?
Oh no, it'll be thousands.
Okay.
But that will include the ones that are pretty far out.
But I mean the close in, like the nice.
Yeah, I'm sure that will be many
dozens,
hundreds.
Probably. Okay.
Yeah.
And we have time for one more quick question.
Yeah, hi. Can you comment on what causes the spokes on the rings of Saturn?
People are asking hard questions. You've been doing your homework or something. Spokes, I'll just sort of, for the people who don't know what even this question is about, back in the Voyager days, we saw some very, very dark lines, sort of broad fat lines, rotating with the rings of Saturn, mainly in the B ring, which is the central, the densest ring. It was very mysterious in the early Cassini mission that we weren't seeing any spokes at all. And then finally, a couple of years ago, they started turning up, and they started turning up in abundance. Seems to be basically a function of the lighting geometry. What happened a couple of years ago is that we went through equinox at Saturn, so we had very, very steep angles, slant lighting on the rings, and that gives you a kind of long pathway through the fine dust that apparently makes up these spokes. But it would also be fair to say that, to the best of my knowledge, I've never seen any convincing explanation for how they work. It's probably some kind of an interaction between impacts into the rings, raising little clouds of dust, and then the magnetic field of Saturn taking over and kind of spreading things out into these linear features. But I don't recall anyone ever having put forward a a model
convincing model.
where people could say, hey, yeah, that sounds like it works, and it explains everything we see. It's still a big mystery.
All right, that brings us to the end of our panel. If I could have everyone thank our panelists one last time.
Wow, silence.
I'm sorry, I didn't know.
No, you're very good. I'm teasing you.
And I'd like to remind everybody one last time that the DVDs are for sale outside, and I hope you stick around for our last panel of SETICon.